Gay-Lussac's law, pressure versus temperature. I'm Mr. B. Gay-Lussac's law states that the pressure of a given mass of gas varies directly with the absolute temperature of the gas when the volume is kept constant. Mathematically, it can be written as P is directly proportional to T, or P divided by T is equal to a constant, where P1 over T1 is equal to P2 over T2, which is equal to P3 over T3, etc., all which should equal the same constant. This means that P over T is equal to K, or P is equal to KT, where P is the pressure of the gas, T is the temperature of the gas measured in kelvins, and K is a non-zero constant. For comparing the same substance under two different sets of conditions, the law can be written as P1 over T1 is equal to P2 over T2, or we may simplify the formula by writing T2 times P1 is equal to T1 times P2. The equation shows that as the absolute temperature increases, the pressure of the gas also increases in proportion. This is an illustration of Gay-Lussac's law, where the temperature and the pressure are a direct relationship. As the temperature on the gas increases, the pressure of the gas increases as well. Consider the following practice problem. Determine the pressure change when a constant volume of gas at 1.00 atm is heated from 20 degrees Celsius to 30 degrees Celsius. First, we must convert the temperatures. In this case, T1 is equal to 293 K, where 20 plus 273 is equal to 293. And T2 is equal to 303 K. The data is written as follows, where P1 is equal to 1.00 atmosphere. T1 is equal to 293 K. P2 is unknown, and T2 is equal to 303 K. In the solution, we arrange the data as follows, where 303 K times 1.00 atm is equal to P2 times 293 K. This is the numerical setup for calculating P2 in this particular case, where P2 is equal to 1.00 atm times 303 K divided by 273 K. The K's will cancel, and the answer is 1.03 atm. A container of gas is initially at 0.500 atm and 25 degrees Celsius. What will the pressure be at 125 degrees Celsius? Once again, we must convert the temperatures to Kelvin, where T1 in this case will be 298 K. This is 25 degrees Celsius plus 273. T2 will equal 398 K. The data is written as follows, where P1 is 0.50 atm. T1 is 298 K. P2 is unknown, and T2 is equal to 398 K. To solve for this particular problem, we arrange the data as follows. 398 K times 0.50 atm is equal to 298 K times P2. To solve for P2, we arrange the data as follows, where P2 is equal to 0.50 atm times 398K divided by 298K. The K's will cancel, and the answer is 0.668 atm. A gas container is initially at 47 millimeters of mercury and 77 K. What will the pressure be when the container warms up to room temperature of 25 degrees Celsius? Once again, we convert the temperatures to Kelvin. In this case, T1 is given as 77 K. T2 is equal to 298 K, which is actually 25 degrees Celsius plus 273. And P1 is equal to 47 millimeters of mercury. The data is arranged as follows. P1 is equal to 47 millimeters of mercury. T1 is equal to 77 K. P2 is unknown, and T2 is equal to 298 K. The solution involves the following arrangement, where 298 K times 47 millimeters of mercury is equal to 77 K times P2. Solve for P2 yields the following, where P2 is equal to 47 millimeters of mercury times 298 K divided by 77 K. The K's will clearly cancel out, and the answer is 182 millimeters of mercury. A gas has a pressure of 699.0 millimeters of mercury at 40 degrees Celsius. What is the temperature at standard pressure, where standard pressure is equal to 1 atm or 760 millimeters of mercury? Once again, we convert the temperatures. In this case, T1 is equal to 313 K. T2 is unknown, and P1 is equal to 760 millimeters of mercury, which is actually standard pressure. The data is arranged as follows. P1 is equal to 699.0 millimeters of mercury. T1 is equal to 313 K. P2 is equal to 760 millimeters of mercury, and T2 is unknown. To solve for T2, we arrange the data as follows. T2 times 699.0 millimeters of mercury is equal to 313 K times 760 millimeters of mercury. The numerical setup for solving for T2 is written as follows. 313 K times 760 millimeters of mercury divided by 699.0 millimeters of mercury. The millimeters of mercury will cancel, and the answer is 340 millimeters of mercury. This concludes my lesson on Gay-Lussac's law, pressure versus temperature. Hopefully this video has been helpful. Thanks for watching.